Welcome back once again to this course on convex optimization. We have over these say 12 or 13 lectures, we have indeed done a lot of things. You must be wondering possibly that now come on, just to find the maximum or minimum of a function which you have done almost waving your hands in high school when in a calculus course, you need so many stuff to do that. But the fact is that you never realize what we are doing in high school, because in that level you do not differentiate between global minimizers, local minimizers, you do not even bother whether you have got the exact solution or not. So, there are a lot of issues involved. Here we are gearing up a machinery which can take on practical problems. Here we are building up a machinery which can answer many diverse type of queries regarding optimization. Here we are building up a machinery which would allow us to develop algorithms. The problems that you have seen in high school or even in your first year math 1 courses across engineering institutes or science institutes is that what you have seen is just very small problems. Real optimization problems cannot possibly be solved by hands, and you therefore need a machinery which would support you to build the algorithm. And of course, we will come to the algorithms very soon. We would soon indulge ourselves in the pleasures of linear programming, which is a very important part of convex optimization. Our aim in this course is clear in the sense that see I would just interrupt here. Once in a while it is good to focus on the aim in a course, but it is not that everything that you plan to tell to the students can actually be done. Always you have ambitious dreams, but you work towards that dream, but you go to a certain level. So, the course as I have envisaged in my mind before I thought of delivering this lecture, that view gradually gets changed, it is changing as I am moving, and I also at the end want to see you learning some modern things with huge amount of applications, things which you can really apply in your own work. So, I am assuming a huge amount of audience from engineering in this course. So, a lot of things would be of help to you as we go through the course. So, in the last class we have spoken about what is called Fenchel conjugate. Now, you see it is very important to know if whether you are having fun or whether you are not having fun. If you are not having fun, then you must leave right now. You must stop seeing this course and just forget about it. But you are having fun, you need to carry along. You have to have a bit of love for mathematics, of course, because this is a mathematical course and I am from the mathematics department. So, I will be more mathematical in my orientation, but be with it if you think that these are finally you will get something which you will need for your other studies like applications or whatever, or possibly you are just enjoying it. So, you do a thing because you need it, or you are just listening to a thing because you are having good fun, just like you see a movie. So, if you are not doing either of the two, leave right now, do not see this lecture, see these lectures. So, now I have defined conjugate, and also there was a promise that I would prove that the polar of the polar cone is the cone itself. So, I now look at what happens if my convex function is an extended valued and proper convex function. it is proper. So, there is no use bringing in minus infinity. So, then also you can define the conjugate in the same way, it does not matter. Now, observe this function would never take minus infinity value, would never take that value. The reason is as follows, because this function is proper. So, domain of f or the effective domain of f, which consists of all x such that f of x is finite, this is non-empty. So, there exists at least one point where f x is finite. So, in that case that will be finite and the supremum would be that value. So, if f x is infinity, then of course, this value would become minus infinity and of course, would not contribute to the supremum. So, you can write for this particular case, you can write this So, you just have to bother about the effective domain. So, when it was finite value, this was R n. This has advantage, putting it in this framework has an advantage. A very fundamental result, which essentially is the structure of optimization, convex optimization in some sense, is the relation between f and f double star. So, f star, if f is proper, and so is f star. Now, just like we have defined polar of the polar of a cone. So, you can also think of defining the conjugate of the conjugate. Now, let us see what is this thing means. You have the conjugate and then you define the conjugate, which acts on x and which is exactly a same definition, just for f star is now the function. Now, you are running over x star element of R n. Now, you see f star itself is a proper convex function, it is extended valued in general. So, here x star is been fixed and your x is been fixed and you are minimizing over x star. So, if f is proper, it implies f star is proper, means it has one finite value, and at one there is one x in R n for which f x is finite. Which I can also write as f star star is proper. There is something bit more interesting that will come out of this f star star business. So, you can ask that you have said that polar of the polar is the cone. So, what is f star star of x equal to? Is it f? Now, that is a good question of course, and we would like to see whether this is true or not. Let us go back and look at the definition of f star star. So, by the definition, of course, I just remind you that this definition I can replace the Rn by domain of F star, which by the way is non-empty. So, it will be x star x minus F star of. Can we infer anything from here? Does not look like it. If you put it, you try to jiggle up the things, it will get more complicated. So, what do I do with it? So, let us go back to F star and see what we have something from there. F star x star is supremum of x belonging to Rn. So, it is the definition of the conjugate given last class. So, there you go. F could be extended value, need not be extended value. You could just think while you are reading this or when you are looking at what I am telling, you can really take F to be finite valued and work. The interesting part of all these things being on the YouTube possibly, as I am told, and there are a lot of these courses on the YouTube, is that you can do replays. It is like reading a book. If you do not understand a thing, you go and read it again. So, this is exactly what you are going to do. You can stop the show and go back again and have a look. It is very important that you go back and follow the trail of the arguments. Now, what do I have from here? If you take any x, this is what I have. Now, let us change the positions. So, this would imply f of x is bigger than. Now, this relation is not only true for all x, it is true for any x star you take. So, for all x and for all x star in Rn. So, for the pair x x star, this result is true. So, I can now just change my position. Once I have changed my position, I am almost in a form where I am in the form of this definition. Now, what I can do is apply supremum over x star, right. So, x, because x star is absent here, so this side will not be affected by the supremum operation. So, these are also classes of affine functions which are lying below f, and what you have proved, what we have proved for any proper convex function, this is nothing but the definition of f star star x star, f star, which is same as I have just written it in the standard way textbooks would write in convex analysis or optimization. So, f x is always, sorry, not x star, this is x, this is the definition of f star star x. So, f, so we know the inequality goes in this way. What about the reverse? Can I prove that if f is proper and lower semi-continuous, then, so if f is proper and lower semi-continuous. So, I do not want to get into this too much technicalities, rather than giving you the ideas. We have f of x is f star star of x for all x. So, this is a fundamental result. So, if you take the supremum of all the affine functions lying below a convex function, then what you essentially get is your f star. So, if you take the supremum of all these affine functions, you take the envelope is f, and by the very definition what we are proving by this thing, what it shows that the upper envelope of this is nothing but f star star, and f star star is actually f. So, let us try to figure out some conjugates. Let me take the function f x half x square, x is in R. Let us see what happens. So, this would be the conjugate is f star x star supremum over x in R. Now, here the inner product is just multiplication x star into x minus f of x. So, basically supremum a very important thing to observe here is that the conjugate function is usually not differentiable, because it is expressed as the suprema of affine functions. Now, if you observe this little fact, then what I have to do is to find the maxima. So, I am gone back to high school, I have gone back to high school mathematics again. So, now I have a function phi of x, where x star is some fixed number and I have to minimize it over x. So, to do that I first have to check the first order necessary optimality condition. Find an x which would satisfy phi dash of x for the derivative of phi at x is equal to 0. So, we would imply that this would imply if I take the derivative of this one, x star minus x is 0 or x star is equal to x. Now, is this a supremum? To do so, you have to take the second derivative of x. If I take the second derivative of x, what is happening? If I take the second derivative, it will become minus of 1 for whatever x you choose. Now, this is strictly less than 0, which implies that x star, x equal to x star is a strict maxima. Here the problem was a concave maximization problem, which is just the opposite. If f is convex, then minus f is concave, or f is concave means minus f is convex. So, this is a concave function whose global minima or local minima are global. So, you have a strict minima. I did not much define what is a strict minima. I will I think we did in the very early days. So, it means that for any x not equal to x star, f of x is strictly bigger than f of x star, that is what it means. Now, so my supremum value is been evaluated at the point x star, and this is nothing but x star, x is nothing but x star. So, this value is x star minus half x star square. So, this is exactly equal to half x star square. So, the conjugate and the function are the same. So, this is the only example where the conjugate and the function are the same. So, your homework would be to now go to a slightly higher dimension, which is n. So, now you take x element of R n and consider the function f x Tell me tomorrow what do you find? Is it the same thing? It would be back to half norm square x or something else? Quite interesting. Another homework, x is in R and I define the function f x is log of x minus log of x, convex function. If x is strictly bigger than 0, and I define this as plus infinity if x is less than or equal to 0. Your job is to find the conjugate, find f star. Here also the question is find f star. Do not need to find f star star, you can find it anyway. Now, let me be curious enough and ask you, f x is equal to the indicator function of C at x, where C is a closed set. So, del C is lower semi continuous and proper. That is, let me try to calculate f star x star in this particular case. Now, you know that whenever x is not in C, this is my plus infinity, and so this will give me minus infinity, and so I really have to bother about those x which are in C, and for those x which are in C this is 0. So, this will be reduced to now. If you look at this expression, this thing where you have a fixed x star and you are varying the x over C, this is called the support function of the set C. That is, this is usually denoted as the support function So, it is a support function. So, sigma C is a proper and lower semi-continuous convex function. Why it is lower semi-continuous? Ponder over this question. Why I am directly writing it is lower semi-continuous? too much of math, I guess, but we will get life going slowly. So, this sigma c, which is called the support function, has an interesting property. Sigma c is convex, of course, and sigma c satisfies this property. If you multiply lambda with x star, then this is nothing but lambda times sigma c x star. Now, you might ask me, hey guy, come on, what would happen if your sigma c x star is plus infinity and you take lambda to be 0. So, I claim that this is this must be this is true. You can figure this out, figure it out, but you have to be cautious. Once you are playing with infinity, it is like playing with fire a bit. It does a lot of good things to you, but you have to be a bit cautious. That's the whole thing. So you figure it out. This is just putting things in the definition, because if you put lambda of x star here, if you take the supremum of linear functions, lambda will just come out. It does not matter, it will be supremum of lambda of f is lambda times supremum of f is if lambda is bigger than or equal to 0. This is a standard thing for the finite valued case. So, this will be true even for this case. Now, you have to be very careful. If lambda this is plus infinity, if lambda is 0, this is 0. Now, if lambda is 0 and suppose sigma c x star is plus infinity, what would be this side? Now, we have to invoke what we have spoken about plus infinity when we introduced extended valued functions. We have said that, with due apologies to all those who do not agree, we would consider lambda into 0 into plus infinity to be 0. So, what we would have is that under our convention that lambda, if lambda is equal to 0, then lambda into plus infinity is 0. This would give me the fact that sigma c of 0 is 0. So, under that convention you get this thing. So, such a function which satisfies these two properties is called a sublinear function, not really linear, slightly linear, and of course, convexity will immediately give you using half, you will immediately get by using this, and this is the following thing. So, sigma c half of x star plus half of y star by convexity of sigma is half of by convexity. So, now I can write this again as sigma c half of x star plus y star is less than half of sigma x star plus half of sigma c y star. Now, by the rule of positive homogeneity, let this rule is called positive homogeneity or non-negative homogeneity, but does not matter. So, this will immediately tell me half of sigma c x star plus y star is less than equal to half of sigma c x star plus sigma c y star. So, this would obviously give me So, this property is called subadditivity. So, if a convex function is positively homogeneous, has this property, then it will have this property. Such functions like the support functions are called sublinear functions. An important example is f x is equal to the absolute value of x. Another further important example is if f is from Rn to R and convex, of course, f dash, the directional derivative at a fixed x, becomes a sublinear function of v as you vary the direction v. So, it is sublinear in v, and this property is so crucial for going beyond convexity. So, we have learned a bit about conjugates, some interesting facts. We will see them later on when we speak about duality theory after a few days, but now let me go back and try to fulfill the promise that I would prove that k star of star is k if k is closed and convex. That is what I promised yesterday, and I am keeping my promise. Because I am speaking to you through electronic media and not face to face, it is quite impossible for me to check how many of you have actually done the job. Some of you might have, some of you might not have, but it is instructive to try. It is not that every thing that you do in mathematics you will succeed in doing a problem, but trying is fun. It is the journey is the goal and not possibly the destination always. So, when you take this attempt to solve a problem, you learn a lot of things by doing that, and that would help you to understand many things in this subject, anything which is mathematical. Now, how you prove that a set A is equal to B? You first prove this, A belongs to B, when A is a subset of B, and then you prove that B is a subset of A. So, that means both A and B are same. That is, every member of A is a member of B and every member of B is a member of A. So, their members must be the same members. Now, take K, take V in K. So, this would imply by the definition of K polar, V of W is less than equal to 0 for all W in K polar. Because it is in K, any W you take in K, by definition W of V is less than equal to 0 for all V in K. So, for whatever V you have chosen, this would be true for any W you take in K polar, that is by definition of K polar, by definition. So, this would imply that V is element of K polar polar, again by definition of polarity of a cone. Now, this would simply mean the following, that I have taken a V in K and got shown that the same V belongs to this. So, K belongs to K polar polar. The next question of course is the following. I am asking you this question: is K polar this is bit tricky. So, let us try take an element V in K polar. So, this would imply V of W is less than equal to 0 for all W in K polar. That is the definition. But that does not tell me that V is in K. It does not. If V is in K, then this would be true. But this no way tells me that V has got to be in K. Every element in K satisfies this, but there is no way I can show from here that V is in K. Is V in K? I do not know. So, this approach, like imitating what I have done, is something which is not going to work. So, what shall we do? So, when a direct looking approach fails, you have to take the indirect approach in mathematics. Proofs by contradiction, however ugly they might look, are possibly the last resort that you have to take. So, let us do one thing. So, I will do a proof by contradiction. So, I will claim, I will assume on the contrary that K polar is not a subset of K. So, there exists a V in K polar, but V is not in K. So, I am assuming the opposite thing. So, I will say that if I assume this, I will reach a contradiction, that is what is called proof by contradiction. Like or dislike, the fact is that we like it or dislike it, the fact is that there is no other way but to resort to this approach, because the direct way, as we have seen, does not give us any conclusion. So, let me see what can be done. So, now V is not in K and K is a closed convex cone. So, you can apply the separation theorem that you learned quite a bit before, maybe some 6-7 class early before. So, you might have forgotten it. So, since it is possible that you have forgotten it, so let us apply it again. So, there would exist a P not equal to 0, P belonging to R n such that P of V is strictly bigger than alpha is strictly bigger than P of W for all W in K. This is a strict separation theorem. So, here we have applied the strict separation theorem. Now, once we have known this fact, what should we do now? Now, this is P, by the way, if you get confused. Now, I can put W equal to 0. Okay. So, then I have P of V by setting W equal to 0 because which is in the cone K. Now, I want to prove that to show that P is in K naught, that is P of W is less than equal to 0. Now, if P of W, P is not in K naught, then if P is in K naught, if P W is less than equal to 0 for all W in K, then P is in K naught. By the very definition, if this happens, it would imply P is in K naught, if and only if. So, if P is not in K naught, then there exists a W dash in K such that P of W is W dash is strictly bigger than 0. Now, W dash is an element of the cone K. So, this means P of lambda W dash is strictly greater than 0 for all lambda strictly greater than 0. Now, as lambda tends to infinity, this will become bigger and bigger and bigger, so big that it can actually cross the value of alpha. So, there would exist lambda naught such that P of lambda naught W dash would be strictly bigger than alpha. In fact, and lambda naught W dash is obviously an element of K. So, this would be in direct contradiction, this and this are in contradiction. So, means I am disproving this fact, but which has to hold by the separation theorem, which means what there is a contradiction means that what I have assumed is not correct, and K polar is also a subset of K, proving that K is nothing but K polar. So, tomorrow we will give some more examples of conjugate functions, talk about something called Fenchel duality, but just give you a hint. But we will tomorrow concentrate on a thing which I am keeping in writing at this moment, saddle point conditions. And that would lead us gradually to the study of linear programming, and we will spend quite a bit of time delving into the pleasures of linear programming. Thank you very much.